2.4. In this lesson, we will learn how to implement dimensionality reduction techniques in MATLAB. In the previous lesson, we just saw techniques to try to visualize the features of the Fisher's iris dataset to try to better understand trends and relationships in the features. Our aim was to gain an intuition about each feature. We saw that to do this, we ultimately created histograms of each feature and scatter plots for different combinations of features. We needed 6 scatter plots to visualize all of the relationships between features. If we consider this to be a Phi-feature dataset, we would need 10 such plots. If we had 6 features, we would need 15 plots. Some datasets could have hundreds or thousands of features or more. Analyzing such a dataset the same way would require lots and lots of plots. How could we feasibly visually analyze the data for such large numbers of features? This is where the concept of dimensionality reduction comes in. In this lesson, you will learn techniques that, given the correct circumstances, allow us to transform information from a large set of features into a new, more compact set of features that are easier to visualize and understand. How does this work? Well, one thing we saw with our scatter plots was that oftentimes different features tend to change together when they are correlated with each other, resulting in a diagonal shape to the data in the scatter plot. This happens when the features are not entirely independent. In the field of mathematics called linear algebra, we learn about independence of vectors in linear vector spaces. Linear algebra teaches us that we can mathematically describe one vector as being linearly dependent with respect to a set of other vectors if that vector is equivalent to a linear combination of the other set of vectors. So, if we have a set of vectors as rows of a matrix Y, we would say that the vector in the first row, y1, is linearly dependent on the other vectors in Y if it is possible to find a linear combination of the set of the remaining vectors in Y that is equal to the first row. What do we mean by a linear combination? What we mean is we can take some scalar multiple of row 2, add it to another scalar multiple of row 3, and add that to some scalar multiples of all the other remaining rows in Y, and the result is equal to x. In this example, 1 times y2 plus 2 times y3 equals y1. Why is this important or useful? If we assume feature samples are normally distributed, which sounds like a big assumption, but is reasonably well satisfied by quite a range of processes, it turns out that if different features are correlated, we can represent the feature space of n features in a reduced linear subspace of m less than n dimensions. In other words, while we have n dimensions of features, those features only vary in m directions. If you're still a little lost, don't worry. We're going to look at a couple of simple examples that illustrate these concepts and make them easier to understand. After we look at these examples, I encourage you to come back to review these initial slides. Okay, let's go to MATLAB. Let's consider a small data set of 4 samples of a process where we measure 2 features. We define our data to be d equals minus 5, 2.5, 2, minus 1, 10 minus 5, minus 12, 6. To inspect the relationship between the 2 features, we do a scatter plot. So we can plot the all rows first column of D on the x-axis, all rows second column of D on the y-axis, and we'll use O symbols. And so that we have appropriate white space around the samples. We set axis to range from -15 to 15 in both the x and the y directions. We can label the x-axis as displaying feature 1 and the y-axis as displaying feature 2. Our scatter plot reveals that our data are perfectly diagonal. This shows feature 1 and feature 2 are perfectly correlated. Because the two features are perfectly correlated, if we are given the value of feature 2 for a new sample, we know everything we need to know to perfectly predict or estimate the value of feature 1. We can see that for every sample, the value of feature 1 is equal to -2 times the value of feature 2. While it is accurate to say we have 2 dimensions of features, since we have 2 features, there are not actually 2 of what we call inherent dimensions in the feature set. The features are organized on a line in the feature space, and a line is a one-dimensional vector space. Mathematically, we can define this vector space using what we call a basis vector. Here we can define our basis vector v as 2 minus 1. We say that V forms a basis for this one-dimensional vector space because the features for each sample are equal to a scaling of this basis vector V. The first sample are features -2.5 times V. The second sample is 1 times V. The third is 5 times V. And the fourth is -6 times V. In other words, instead of representing each of our samples by 2 features, we can represent each sample with a single feature number that is a coordinate in our one-dimensional linear vector space defined by our basis vector V. Our set of samples in our new linear vector space have coordinates A equal to -2.5, 1, 5, and -6. With these subspace coordinates, we can return to the original feature space coordinates by multiplying A by our basis vector V. And so we can see our entire data set D is representable by a scalar multiple of our basis vector V. This is an example of dimensionality reduction. We have reduced the number of dimensions of our feature set from 2 to 1. And we can do this because the 2 features are correlated. We can also vary the scale on the basis vector. This generates new synthetic examples of feature measurements. While our actual samples we started with only include 4 instances, if we assume our data are normally distributed, we can take a guess at what new instances might look like by scaling our basis vector. Let's plot different scalings of our basis vector. First, we define a range of scales from -10 to 10 in step sizes of 0.25. We can define a unique color for each data point in a color map using the built-in jet color map in MATLAB. This creates a matrix of RGB color codes ranging from blue on the first row to red on the last row. Then we use a for loop to plot each scaling of our basis vector as an asterisk with color defined by CMap. we plot an at I times v1 as our x-coordinate, an at I times v2 as our y-coordinate. We use the asterisk symbol, and we'll plot it with color equal to our color code in CMAP in the ith row. This gives a line of asterisks in our plot that are red for negative scalings of our basis vector and blue for positive scalings. Let's look at one more example of dimensionality reduction with a three-dimensional feature set. We'll define D is equal to -2, -8, -7, -1, -3, -3, 4, 0, 6, 1, 5, 4, -2, -4, -5. Can we tell by looking whether this three-feature data set is inherently 3D, 2D, or 1D? Well, it's fairly obvious that we can rule out 1D because it's pretty clear we can't take one vector and scale it to create the other vectors. But 2D versus 3D, that's difficult to tell. What if we try the following basis vectors? v1 equal to 1, 1, 2. And v2 equal to 1, -1, 1. Then, if we take -5 times the first vector plus 3 times the second, we get our first feature vector, -2 times v1 plus 1 times v2 gives us the second feature vector. 2 times v1 plus 2 times v2 gives us the third feature vector. 3 times v1 minus 2 times v2 gives us the fourth. And minus 3 times v1 plus 1 times v2 gives us the fifth. So we can see this three-dimensional feature set actually lies entirely in a two-dimensional subspace defined by the basis vectors v1 and v2. A 2D subspace of a three-dimensional space is a 2D plane cutting through the 3D space. We can use MATLAB for 3D visualization using the plot3 command. So here we show each feature of the individual samples in the 3 dimensions. We can also define a plane using v1 and v2, describing the 2D subspace that the data points lie within. We can define a square, which is 4 line segments, to represent the plane. The 4 corners of the square will be v1 plus v2, then v1 minus v2, then minus v1 minus v2, then minus v1 plus v2. Then we connect back to the original corner at v1 plus v2. To make the square a little bit larger, we can upscale it by multiplying it by 5. Now we can plot the square. Using plot3, and to show it as green line segments we use the G character. Before we execute the plot function we need to do hold on so that our red data points persist in the plot. And by using the rotation function in the window, we can easily see that all of the red data points fall within this plane, showing how even though we have 3 features, due to correlation among the features, our feature space can be more compactly represented within a simpler 2D subspace. Okay, so now we have a sense for what dimensionality reduction means, but the next question is there a way to algorithmically find these basis vectors to represent the compact linear vector space? In these examples, I was able to take a guess at the basis vectors. For large dimensional datasets, such a guess and check approach is not possible by most mere mortals. Further, if it isn't possible to reduce the dimensions without some loss of information, and yet we still want to only keep n out of m dimensions, is there a way to find the best vectors to represent the space? For example, in our example, we saw all our 3D data fell cleanly on our plane. But what if our data were close to planar but not quite? The plane would still define the principal dimensions of variation, but not all of it. Is there still a way to find this plane, or in the general case, the n-dimensional subspace that captures the greatest amount of information about how the m-dimensional data vary in the more compact n-dimensional subspace? The answer to all of these questions is yes, and the solution is one and the same. A type of data analysis called principal components analysis, or PCA for short, is an extremely powerful data analysis framework that lets us do a number of common data analysis tasks, like dimensionality reduction, missing data prediction, and classification. It's important to know a little bit of technical detail about principal components analysis in order to understand how to use it and what it can do for us. At a high level, principal components analysis is fitting an n-dimensional hyperellipsoid to our n-dimensional dataset. An n-dimensional hyperellipsoid is the n-dimensional equivalent to an ellipse in 2D. The 3D version of an ellipse is an ellipsoid, and beyond 3D, we refer to higher dimensional versions as hyperellipsoids. Principal components analysis assumes that our n-dimensional feature data points are sampled from a process that can be well modeled as an n-dimensional hyperellipsoid. These would be processes that are representable with a mean feature vector that has variance from the mean in principal directions. In other words, this process is well described by a multidimensional Gaussian distribution. If there are any directions in this n-dimensional space where the data do not vary, the feature vectors lie on a lower dimensional hyperplane within the n-dimensional space, and we can simplify or reduce the dimensions of the feature space. As shown in the example above, if we have 3D feature data that only exist on a 2D plane in the feature space, then we can use principal components analysis to fit a 2D ellipse to the 3D feature data. To gain intuition on how this works, let's consider a two-dimensional example. Let's define a 2D data set with 4 samples as d is equal to 5.5 minus 4 minus 1.5, 2 minus 9, 2, 5, 0. And let's plot it in figure 1. We plot the first feature on the x-axis and the second feature on the y-axis. We will use a blue O for the plot and make the line thickness a bit thicker than the default width of 1 so that the O's are nice and clear when we plot some other things on the same figure later. We can set the axes to range from minus 15 to 15 in the x and y directions. We can also label the axes. To make sure the aspect ratio is correct in the x and y directions, we can use the axis equal command. This ensures that the distance along the x and y axes is represented with the same number of pixels on our screen. Next, we use MATLAB's PCA function to find the principal components of the dataset. These principal components are the axes of the ellipse. We call these eigvects, which is shorthand for eigenvectors. The principal component vectors of the data are mathematically what we call the eigenvectors of the covariance matrix of our data D. The magnitude and variance of the data along each of these principal components are called the eigenvalues, and these are returned in the eigvals variable. We mentioned that PCA is fitting an ellipsoid to the data. In this case, with 2D features, it is fitting an ellipse to the data. Let's take a look at what we mean by this. The first eigenvector is in the first column of eigvects. The eigenvector that's in the first column has the largest corresponding eigenvalue, which is the first value in eigvals. The eigenvalue tells us the variance of the data along the direction defined by the eigenvector. Thus, the first eigenvector corresponds to the axis of the ellipse that is longest. Let's plot the long axis of the ellipse, which is defined by the first eigenvector, with a length of 2 standard deviations from the mean, where the standard deviation for the mean is defined by the square root of the variance, which is captured by the eigenvalue. The same thing for the y dimension. This is equivalent to plotting the eigenvector over the range plus 2 times the square root of the eigenvalue to minus 2 times the square root of the eigenvalue. The first vector argument in the plot is the x-coordinates of the 2 endpoints of the line, and the second argument is the y-coordinates of the 2 endpoints of this line. We'll plot this using the R in apostrophes to plot it as a red line. As we can see, we plot a line that visibly agrees with the direction in the feature space where the data are the most spread out. Next, let's plot the second eigenvector. The second eigenvector will be orthogonal to the first one, which means it will be at a right angle to the first one. And again, the eigenvalue will tell us how much variance there is in this direction in the dataset. Here we see an orthogonal line that is much shorter than the first one. That's because our data have less variance in this direction than in the first eigenvector direction. We can also plot the ellipse that is implied by these two principal axes. First, we define an angle variable theta to represent angles from 0 to 2 pi around the ellipse, sampled at a rate of 0.05 radians. Then we define the shape of the ellipse using the equation for an ellipse. First, the x-coordinates in ellipse x will be the radius, 2 times the square root of eigenvalue 1, multiplied by the x-direction component for the long axis vector, which is the x-coordinate of eigenvector 1, multiplied by cosine of theta. Then we add the second radius, which is 2 times the square root of eigenvalue 2, multiplied by the x component of the short axis vector in eigenvectors 2, multiplied by the sine of theta. The y-coordinates of the ellipse will be almost identical to the command for the x-coordinates for the ellipse, except we use the y-components of the long and short axis vectors in the eigenvex matrix. Finally, we plot the ellipse simply using the plot command with the ellipse x and ellipse y coordinates as arguments, and the k dash dash string will plot it as a dashed black line. This clearly shows how by interpreting the principal components as the long and short axis of a 2D ellipse, we are effectively fitting an ellipse model to our data. PCA works not only in 2D, but in n dimensions. So, identically to this example, if we provide PCA n-dimensional data, it will return the n-dimensional eigenvectors and eigenvalues that describe the principal axes of an n-dimensional ellipsoid fit to the data. The eigenvectors and eigenvalues are ordered such that the most important principal axes, that is the ones that capture the largest variance, are first. The last eigenvectors correspond to the shortest axes of the ellipsoid, which are the least important, and the data show the least variance in these directions. We can have both lossy or lossless dimensionality reduction depending on the dataset. Lossless dimensionality reduction is the removal of dimensions in which there is no variance in the data. In this case, the data fall on a lower dimensional hyperplane of the n-dimensional space. In the case of 2D space, a lower dimensional hyperplane would be a 1D line. In the current example, our data do not fall perfectly onto a 1D line, so lossless dimensionality reduction is not possible. However, if we need to reduce the data to one dimension while preserving as much variability as possible, PCA makes this very easy. To show how to do this, let's repeat our call to PCA, but this time using the second output argument. Here, dPCA is an output that contains the coordinates of the samples in the PCA linear vector space. In other words, we define a coordinate system using the ellipse model, where the first coordinate is the distance from the centroid of the ellipse to the data point along the long axis of the ellipse, and the second coordinate is the distance from the centroid to the data point along the short axis of the ellipse. We can visualize these two coordinates in our plot. First, let's draw a line from the origin, coordinate 0, 0, to the PCA coordinate along the first principal component. First, the x coordinates going from 0 to dPCA 1, 1 multiplied by the x component of eigenvector 1 then similarly the corresponding y component. Which uses the y component of eigenvector 1. We can draw this with a green line. As you can see, we get a green line from the origin tracing along the first principal component to the location on the long axis of the ellipse closest to the first data point in D at 5.5 minus 4. Next, we can plot a line extending from the origin tracing along the second principal component to the location on the short axis of the ellipse closest to the first data point. This looks similar to the previous plot command, except we use the second coordinate and the second eigenvector. And we get the distance along the short axis to the first data point. So if we add these two together, we can recover our first data point. We'll draw this in magenta. And we can see now that the first row of dPCA are the coordinates for the first data point in the coordinate system defined by the principal axes. So when we multiply the first axis by the first coordinate and the second axis by the second coordinate and add them together, we recover the xy position of the data point. Now let's say we need to reduce the dimensions of our data set from 2D to 1D, and we'd like to preserve as much variance in the data as possible. PCA tells us that the direction of greatest variance is along the long axis of the ellipse, and the direction of smallest variance is along the short axis of the ellipse. Thus, dimensionality reduction can be accomplished by setting the PCA coordinates to 0 for the second principal component and just using the PCA coordinates for the first principal component. In other words, we can just use the first column of dPCA multiplied by the first eigenvector and ignore the data corresponding to the second principal axis. Note that we still have data that vary in the x and y dimensions, but the intrinsic dimensionality is now 1D. When we plot these 1D results, we can see that they all fall on the principal axis. As we can see in the plot, the reduced dimensional data points fall on the principal axis of the ellipse at the positions closest to the original data points. This is an example of lossy dimensionality reduction. Now let's take a look at what happens when we take our 1D data in D1D and try to run PCA analysis on it. we can see that our eigenvalues are now about 50 and 0. This indicates we have a variance in the data of about 50 along the principal axis and 0 variation on the secondary axis of the ellipse. Since the width of the ellipse on the short axis is 0, our 2D ellipse is collapsed to a 1D line. Thus, even though the data vary in the xy plane, we can immediately see from PCA that the intrinsic dimension of the data is 1D, and all of the variability in the data is along the first principal component. Accordingly, when we inspect dPCA, we see our coordinates in the PCA space are non-zero only in the first dimension. This is now an example of lossless dimensionality reduction. The data points can be represented with no loss as a 1D coordinate along the first principal component vector. One extra important note about the PCA function here. If the mean of each feature in the input data matrix is not 0, the PCA function will demean or subtract the mean from the data. This is done so that the center of the hyperellipse lies at the centroid of the mean value of the dataset, and the principal components then describe how individual samples vary from the mean. In the example so far, the mean value of each feature in the data was already 0. But in case that is not the case, we can have PCA output the mean value it is subtracting from the data to compute the principal components as the sixth output assigned to variable mu. For example, if our data do not have a mean of 0, but instead have a mean of 5, we can still compute our eigenvectors and eigenvalues and output mu in a sixth output. And we see PCA tells us mu for this data set is 5, 5. Then if we want to reconstruct our data from the PCA coordinates in dPCA, we take a linear combination of the eigenvectors scaled by our PCA coordinates, just like before, but we add that back to the mean values of the features that are stored in the mu variable. We can use retmat to repeat the mu vector over the 4 rows. Comparing that to D2, we see that by adding mu to the eigenvector scaled by the PCA coordinates, we're able to reconstruct our data set. Okay, so at this point, I think we have an intuition about how all of this should work. So let's try it on a higher dimensional data set. Loading back in our Fisher's iris data set, we can run PCA on our measurements matrix. Remember, our eigenvalues tell us how much variability we have in each principal component in our PCA model. We can see we have 4 components, and the last couple of numbers get pretty small. Oftentimes we look at the eigenvalues in terms of percentage of total variance. To find the total variance in the data, we take the sum of the eigenvalues. Dividing our eigenvalues by this sum gives us the fraction of variance contributed by each principal component. And multiplying by 100 turns this fraction into percent variance from each component. Now we can see the first component accounts for over 92% of the variance in the data. Thus, a 1D approximation to this 4D dataset captures most of the feature variance. The second captures another 5%, and the last two have a relatively small amount. Oftentimes we ask, how many principal components do I need to capture a certain percentage, say 95% of the variance in the data? If we compute the cumulative sum, this becomes easy to see. With just the first two principal components, we have nearly 98% of the variability in the data. This means that this 4D feature set fits quite well with small loss into a 2D hyperplane in the 4D feature space. So we can make a two-dimensional plot of the first two PCA coordinates for this data set, and this plot should nicely represent the variability in the 4D data set. We'll plot unique symbols for each species. So we need our species label. Then for the first species, on the x-axis, we can plot the PCA coordinates in the first PCA dimension, and on the y-axis, the PCA coordinates in the second PCA dimension with red circles. Then we do the same for species 2 with green X's, and species 3 with blue asterisks. We can label our axes. And so now we can see we have a much more compact representation of these data than the 6 scatter plots we used to try to interpret this data set previously. We can also show the third dimension, as it's possible to visualize 3D data in MATLAB. We simply provide the third PCA dimension as a third argument to plot 3. And similarly for the second species, with green X's, and third species with blue asterisks. And we can label our axes. And using the rotation feature in the plot, we can look at the data from different angles. And we can see that the third PCA feature dimension really does not add much descriptive power to the visualization over using just the first two features. The fourth dimension corresponds to the smallest direction of variance, so it would be even less useful. Oftentimes, high-dimensional data can be well represented in very few dimensions, making PCA a very valuable tool, not only for visualization, but for other analysis tasks as well. We will look at how dimensionality reduction methods in PCA can help not only with visualization, but also with classification and prediction methods in the following lessons. Related to dimensionality reduction is the concept of feature selection. Feature selection is a bit more of a straightforward concept than dimensionality reduction. As opposed to the PCA approach of looking at a set of features and trying to find a more compact subspace for those features, feature selection takes a more problem-specific approach. Consider a dataset D. If the task at hand is classification or prediction of a response variable y, and training data are available, that is, we have a data set of examples with feature measurements in X, as well as the correct answer for the classification or value that we would like to predict or estimate, y, then feature selection aims to choose a subset out of the available features that is most useful in estimating the class or value of interest. The most straightforward way to do this is through linear regression modeling. Simply put, we define a linear equation that is a function of each of the input features and choose the scalar weighting of each feature in our linear equation, b0 to b3, that minimizes the squared error between the estimation and the target value in the training data. One critical benefit of this approach is that statistical tests tell us which features are most significantly contributing to the accuracy of the prediction, and thus this process can be used to select the most important features. On the other hand, we can determine which features are not correlated with the target data, as well as features that are redundant, so that those features can be removed from our feature set. Let's consider another simple example data set to see how this works. This is a set of 6 samples from a 4D data set. D is equal to -2, -8, -7, -6, -1, -3, -3, -2, 4, 0, 6, -4, 1, 5, 4, 4, -2, -4, -5, -2, -4, 2, -5, 6. Let's take our fourth column of D and assume that this is the value of some process we want to predict. We call this our response variable, y. The features we want to use as predictors for our response variable are the first 3 columns of D. However, the last 2 columns of D are actually linear combinations of the first 2 columns. The third column is equal to 1.5 times column 1 plus 0.5 times column 2. And y is equal to column 2 minus column 1. So one of our predictor features is redundant. Let's define our feature matrix X. We'll also introduce a random noise feature to demonstrate feature selection with an uncorrelated feature. And if we're selecting our features properly, the random noise vector should be ignored, as well as one of the other features, which is redundant. We'll also add a little bit of noise to our features in D so that they are not perfectly correlated and perfectly predict our response variable in this example. We'll use RNG 0 to seed our random number generator so that we have repeatable results. Next, we can fit a linear model mapping our features in X to the output in Y using MATLAB's fitlm function. The result shows us that fitlm has created a linear model to predict Y as a function of a linear equation with a constant term called the intercept plus a linear combination of the four features x1, x2, x3, and x4. The first column of the table under estimate provides the scalar multiple of each term in the linear model. Thus, our equation is y is equal to a constant, 0.06, plus feature 1 times 0.01, plus feature 2 times minus 0.44, plus feature 3 times 1.19, plus feature 4 times minus 0.36. The rightmost column contains a p-value for each term. This is a statistical p-value that represents the probability that the contribution of this term with the estimated coefficient leads to a model that is statistically significantly more predictive of y than a model without this term. When the p-value is greater than 0.05, traditionally we would conclude that this feature does not significantly contribute. Here we see only one term has a p-value below 0.05, and the rest do not. However, just doing a one-pass fit of the model with all terms and inspecting the resulting p-values is not best practice for feature selection. The problem is that if several features are good predictors of y, but they are correlated, it is possible that the most predictive features will appear to be insignificant due to contribution of other correlated features in the model. So, even though the terms for x1, x2, and x4 have p-values greater than 0.05, we cannot yet conclude that these terms are insignificant. However, we can conclude that there is redundancy somewhere in our feature set, and that our feature set could be reduced. The most common approach for feature selection with linear models is called stepwise regression. With stepwise regression, features are added or removed one at a time to attempt to find the largest set of most predictive independent features while eliminating less predictive redundant ones. MATLAB has provided a routine to perform systematic stepwise regression called stepwise LM for stepwise linear model. The result is that stepwise will tell us which features out of the input features are most significantly associated with the response variable y, and removes features that are uncorrelated or redundant. As expected, the method correctly identifies feature 1, the random noise vector, as not being significant, as it does not appear in the model. Further, it finds features 2 and 3 are statistically significant with p-value less than 0.05, while removing feature 4 as a redundant feature. Thus, if we would like to train another type of classifier or predictor, features 2 and 3 could be selected as training features while ignoring features 1 and 4. We will see examples using this feature selection approach in following lessons on data prediction. In summary, dimensionality reduction and feature selection methods provide a way to obtain simpler feature sets. This makes the dataset easier to visualize, and additionally, using the best features typically results in improved analysis of the dataset. When we have high-dimensional datasets that are difficult to understand, these techniques can play a critical role.